Two planes are parallel if and only if their normal vectors are parallel. In terms of the equation for these planes, it means they have the same coefficients for the variables x, y, and z, but different constants on the right-hand side. So planes which are parallel will never intersect. But if they are not parallel, then they will always intersect, and their intersection will be a line. So how do we go about finding that equation for the line given equations for the two planes? Well, first we need to find a vector in the direction of the line. So if this vector goes through both of these planes, then it must be orthogonal to the normals of both planes. So then taking the cross product of the normals will tell us the direction of this vector. So then we just need to find one point on the intersection, and that we can do by solving a system of equations. This is best seen by example. So consider the planes x plus 2y minus z equals 2 and x minus y plus z equals 3. Let's see how to parameterize their line of intersection. So our normal vectors for the planes we can see are 1, 2, -1, and v is 1, -1, 1. So that's just the coefficients on the left-hand side. So then their cross product will give us a vector that is parallel to the line. So let's find that cross product. 1, 2, -1, 1, -1, 1. And that is I minus 2j minus 3k. All right, so now we know that the line will have parameterization of the form x equals t plus x0, y equals -2t plus y0, and z equals -3t plus z0. So now we just need to find what these constants are. So the line is going to hit, in particular, every x value at least once, and you could do this with either of the other coordinates as well. So let's choose x0 to be 0 and t to be 0. So then if we decide to pick and let our x0 be 0, then we would get the equations 2y0 minus z0 equals 2 and -y0 plus z0 equals 3. And so you add these two equations together, you get y0 is equal to 5. And then if we substitute that back into the previous equation, we get z0 is equal to 8. So our parameterization for the line is x equals t, y equals -2t plus 5, and z equals -3t plus 8. And again, you could have gotten a different parameterization for this by using setting one of the other variables to be 0 or another number. Again, so parameterizations are not unique, but this is one that you could get. Next, what about finding the intersection between a line and a plane? So this plane is given to us with normal vector I minus j plus k and a point 1, 0, 1. So that means the equation of the plane will be x minus 1 minus y plus z minus 1 is equal to 0. Now we plug in the values of the parameterization of our line, so that'll become 2t minus 1 minus t minus 1 plus 3t plus 2 minus 1, so 3t plus 1 is equal to 0. So now we can we move all the constants to the side, so we regroup, and we get 4t is equal to, this is -2, that's -1. So t is equal to -1/4. So we now put that back into the equations for the line. So we get the line and plane intersect at -1/2, -5/4, and that'll be -3/4, so 5/4. Finally, what if we were asked, does this line intersect the given plane? So let's calculate so the vector parallel to the line is 2, 1, 3. And if we dot that with the normal vector of the plane, in this case, we get 0. So the line and the plane are parallel to each other. So now we'll have one of two situations. One will have, so this is a line in the plane parallel to our line, but our line is above the plane and will never intersect it. Or the line is entirely contained within the plane, in which case the intersection is just the entire line, as opposed to being a single point. So let's see what happens if we go about solving this like we were doing before. And so this will be how we figure out which one is the case. So the equation of our plane is x minus 1 plus y minus z minus 1 is equal to 0. And now we plug in the expression for the line. We get 2t minus 1 plus t minus 1 minus 3t equals 0. But now all the t's cancel out, and we're left with -2 is equal to 0. So this is not true, so the line and the plane can never intersect. So no, they do not intersect. Another way to think about this is to say, well, if the line is inside the plane, then any particular point on the line, if we take that and we take the point P, then this vector must also be in the plane, and in particular will be orthogonal to this. So we could calculate, if we take t equals 0, we get the point on the line 0, -1, 1, and we subtract p from that, and then we would get -1, -1, 0, but the dot product of that with the normal 1, 1, -1 is equal to -2. So this is not 0, and so this is just another way of thinking about why the answer is no. But on the other hand, let's say we change this problem to z equals 3t minus 1. So now the minus 3t is going to become minus 3t minus 2. And so we'll actually get 0 equals 0. So instead of always being false, this equation is always true. So the line, in this case, will be a subset of the plane. And the way that would work down here in this other way of thinking about it is this would become -1, then this would be -2, and so then we would get 0, indicating that, yes, this vector between the point on the line and the point P is inside the plane. Therefore, the whole line must be inside the plane.